tonight's lecture. As I mentioned, hang on, sorry. Let me just check the chat real quick. No, I wouldn't do the knowledge check right now. I would wait until you have a fresh mind. I mean, if you're used to being up this late, I wouldn't do the initial knowledge check if you're tired. Because you want to have a fresh mind to do that. So that you can do the best on it possible. And so now what we're going to do is we're going to do our lecture of our 2 sections tonight, and then we will call it a night, open the floor for any questions, and then you guys can also do the knowledge check if you feel like you're ready to, but you won't be able to get onto any of the homeworks till after you've taken that knowledge check, so they know where you stand knowledge-wise, okay? So in section 1.3, we're going to talk about relations and functions, okay? And so you should be familiar with ordered pairs. That's where we have a x coordinate and a y coordinate, and it's called a relation in x and y. Okay. The x value is called the domain of the relationship or the relation, and the y is called the range, right? So you could think of it when you're asked what is the domain, think to yourself the question. You could say, what values can x be? If you're talking about the range, what values can y be? Okay. And then the definition of the function is really just, given that we have this ordered pair, we say that y is a function of x. And you think of that because our x is our input, our y is our output. Okay. And so we can determine that if for each value of x in the domain, there can only be one y value in the range. Otherwise, it is not a function, okay? So every x has to have only one y. All right, so let's look at some examples that we have here and determine if these things are functions or not, okay? So here we can see that we have 2 x values that are equal to 2. One of them has a y value of 3, and the other has a y value of 4. So in this case, we have the same x, but we have different y's. Therefore, no, this is not a function. Okay. For this next one, we have 1, 2, 3. We have no repeated x's. Therefore, every x goes to a unique y. And so, yes, this right here is going to be a function. You could see things displayed graphically like you see here, where we have 2 circles and the arrow. You can see each one of these x's go to exactly one y. Now, if this had said something like this, where -2 went to -2 and 6, then that would not be a function. But we don't have that case, so this here is a function because every x maps to exactly one y. Okay? Question. Cindy, did that help the explanation in the chat help? So if the same x goes to 2 y's, it is not a function. Okay. So every x has to go to only one unique y. Okay. So in this next problem, if I put in 1, I get out 8, right? Input 1, output 8. Input 2, get a different answer. Input 3, get a different answer. Input 4, get a different answer, right? So every X gives me a unique Y. So yes, this is a function. Okay, I'll put that here. Every X gives a unique Y. Kind of how you could think of it. Exactly. You cannot have a repeated X, but you could have a repeated Y. So, for example, if I had, in this case here, you could see this here repeats, right? But this here is a different X, different X's, same Y. It's okay. It's still a function. We'll learn later about what's called a one-to-one function, and that means every X has to have a unique Y, and every Y has to come from a unique X. But that's a one-to-one function, and it's a special type of function. But when we're talking about functions in general, every X has a unique Y. Okay? And then here, if I put in 1 squared, that gives me a value. If I had negative 1 squared, it gives me a unique value. No matter what I put in for X, I'm only going to get out one value for Y. So that is also a function. Okay. This next one, if I put in, we could rewrite this where it's Y equals 7 minus X. So every value of X that I put in, I'm going to get exactly one unique Y. So yes, this is a function. Okay. This next one, if I do this, I get Y squared is equal to 7 minus X. I'm going to take the square root of both sides, and I get Y is equal to plus or minus the square root of 7 minus X. So let's just say, for example, I said if X equals 3, right? I plug that in, I get Y equals plus or minus the square root of 7 minus 3, which equals plus or minus the square root of 4, which means plus or minus 2. So when I put in X, I get out a positive 2. But when I put in X, I also get out a negative 2. So you can see 1X produces 2 Ys. So no, this is not a function. Right? 1X. Let me do a different color. Okay? Question. Okay? This last one, we end up with Y cubed equals 7 minus X. We take the cubed root, and a cubed root is fine. That is why it's not like a square root. So a square root, a fourth root, a sixth root, those are going to be not functions, but your odd ones will be functions. Okay? All right. So we have another way to help us determine if something is a function or not, and it is called a vertical line test. So a vertical line test means that if I can draw a vertical line, multiple vertical lines across my graph, and it does not intersect in more than one location, then it is a function. if the line crosses my graph more than one time in a single vertical line, it is not a function. Okay, so take, for example, I'm going to come here and I'm going to just draw these lines, right? And you can see right here, I cross my graph here and here. This is not a function. On this one, we draw these lines, right? And you can see I've crossed once, I've only crossed once. Each vertical line only crosses my graph one time, so yes, this is a function. Okay, what about here? We're graph, line, right? Vertical line. I see I have a cross here and I cross here, so no, this is not, because even though it only occurred in those two locations, it means that it's not a vertical line. Okay, now let's say, for example, that this had been, let's say that this had been a hollow dot, not a solid dot. Hollow means it is everything up to that point, but not including that point. Then when we do our vertical line test here, it only crosses in one because this is hollow and it doesn't include that point. So then, yes, that one would be a function. Okay, question. Right, so now we're going to move on to evaluating some of these functions. And by the way, by having this lecture of 2 class stuff, it should make this sort of material a little easier on the, as a refresher for when you do the initial knowledge check. And so hopefully it'll eliminate some of the work that you have to do for this week. All right, so we want to evaluate this function, f of x equals 2x squared minus 3x plus 1. And we want to do it for these given values of x, okay? So this one is f of -3. So that's telling me everywhere I see an x in that function, I'm going to substitute into it this -3, okay? So I have 2. And I have this x, so now I'm going to substitute in a -3 squared minus 3 times -3 plus 1. Okay? So this equals 2 times -3 times -3 is 9. Minus 3 times -3 gives me a positive 9. And then we have this plus 1. Now we have 2 times 9, that is 18 plus 9 plus 1. And when we simplify all of that, we get 28. So when I plug in -3 into that function, I get out positive 28. Questions?
For our calculators, are there any specific settings we have to have?
No, did you try to do this one in a calculator?
Yeah, and it got it wrong, so I was just making sure.
What it is, perhaps, in the calculator, you probably would need to do it 2 times parentheses -3 parentheses caret 2 minus 3 parentheses -3 parentheses plus 1. See if that helps you. They may also require that you put the multiplication here.
Yeah, that worked. Thank you.
Yep. So because of the order of operations, it's very important that when you do put things like this into your calculator, that you get the parentheses right. Otherwise, because if you didn't put the parentheses, if you had put -2 times -3 squared, right? It's not going to do -3 times -3. It's going to do -3 times 3 because the squared is only on the 3 and not on the negative as well. And so that's why the parentheses are really important. Okay. All right, so let's look at the next example. The next example we have x is the square root of 2. So in this one, that would be, and I like to use lots of colors. So if I ever use a color that somebody might not be able to see very clearly, definitely just say, hey, don't use that color, please. I have a hard time seeing it, or whatever. And if you don't want to speak up in class, send a little note in the private, because I can always do this, right? Oh, you can't see that green. That green's hard on your eyes, and I can change it to purple. Okay. So I don't want any barriers. The math is hard enough to learn. I don't want there to be any other additional barriers for you guys. All right, so let's use the f of square root of 3. So this is going to be f of the square root of 2, I said 3, but it's 2, is 2 times the square root of 2 squared minus 3 times the square root of 2 plus 1. Anytime I do the square root times the square root, it makes those go away, right? So think of this, and I'll often do little side ideas over here. So if I have the square root of 2 times the square root of 2, that's really the square root of 4, which is 2. Okay. So you could think of it like that, or you could go, oh, I have 2 square roots. The square roots cancel each other, and it just leaves me with one of the insides. So that's going to give me 2 times 2 minus 3 square roots of 2, because there's no lowering that or anything, plus the 1. And so we only have one more step to do, and that's 2 times 2 is 4 minus 3 square roots of 2 plus 1. And then the last combination that we could do here is 4 plus 1 is 5 minus 3 square roots of 2. So this one you're not going to be able to do on a calculator, right? Because your calculator's not going to give you that what the exact square root is. So it's important, remember, you have to show your work on your exam. I wouldn't make you do all of these. I would make you show this, right? And maybe you need to put an intermediate step, maybe you don't. Because I'm trying to help you all learn, and we're not all at the same level at this point, I try to put as many steps as possible so that all levels in this class get some benefit out of it. Okay. All right. Any questions? So this next one is we're substituting the letter A. So this is f of A equals 2a squared minus 3a plus 1. And technically, we could have written it in the parentheses to stay in true form, and then simplified it just to be 3a squared minus 3a plus 1. Okay, questions? The last one is f of 3 plus z. Okay, so this is f of 3 plus z gives me 2 times 3 plus z squared minus 3 times 3 plus z plus 1. Okay, so we have to simplify this. We have 3 plus z squared is 3 plus z times 3 plus z. We use FOIL, so we're multiplying our first and then our outers, right? And that's going to give us 9 plus 6z plus z squared. Okay, so that is 2 times 9 plus 6z plus z squared. This we can just distribute. The -3 times 3 is -9. -3 times z is -3z. And then we have that +1 out there. Okay. So simplify. Now we can multiply this 2 by each of the terms here. So we're distributing that 2. That gives us 18 plus 12z plus 2z squared minus 9 minus 3z plus 1. Now all we need to do is combine all of our like terms, starting with the highest exponent number. So we have 2z squared. So that takes care of this one. Now we have the z's. So we have 12 minus 3. So that's going to give me 9. So plus 9z. And then our constants, we have 18 minus 9 is 9, plus 1 is 10. Okay, so when we evaluate that function at x equal to 3 plus z, we get 2z squared plus 9z plus 10. 3, where the 3 where?
On the x equals a, why the answer is 3a squared and not 2a squared?
Thank you. That's a typo. Okay. Question. All right. Making sure I don't have any more down here. All right. So now let's evaluate where we have under the radical, right? So a couple of things. The radicand, the thing underneath that radical sign, must be positive. It must be greater than or equal to 0. Otherwise, it's a complex number, imaginary, and we're not dealing in imaginary numbers at this point in the course. Okay? So, but keep that in mind. You guys probably remember from algebra days that if you remember the square root of -1 is equal to I and that sort of stuff because it's imaginary, that sort of stuff. We're not doing that at this point, but just know that everything under the radical has to be greater than or equal to 0 or it is undefined. Okay. So when we look at evaluating this at G of 3, so I mean, so let me make this a G and F here since all my problems say F, sorry. Okay, so F of 3, we're going to evaluate it here. So F of 3 equals, get a color. F of 3 equals square root of 6 minus 2 times 3. That equals the square root of 6 minus 6. Square root of 0 is 0. So when we evaluate that problem at x equal to 3, then we get a solution of 0. Okay. What if we evaluate it at 4? So we take the square root of 6 minus 2 times 4. That is the square root of 6 minus 8. which equals the square root of -2. And as I mentioned, our radicand must be greater than or equal to 0. And so since it is not greater than or equal to 0, it is undefined. Okay. Question. Let's look at -4. So that is the square root of 6 minus 2 times -4. That is 6 plus 8. Okay. 6 plus 8 is 14. And so we can look at this and say this is 2 times 7. We can't simplify this anymore. So the square root of 14 is our solution. Okay. Question. Okay, so for the last one here, we have 6 minus 2 times 2w. That is square root of 6 minus 4w. And we can't simplify that any further. That's as far as we can take that. Okay, question. Okay. So now let's talk about x and y intercepts. Okay. Remember whenever I graphed that example problem when we were going through the tour of Alex, and I was like, oh, my y-intercept, that's this. I knew where to put that because I could look at the equation and draw that out. By the, in this course, you're going to get to the point where you can do that as well. If you don't already have that, you probably already got those sort of things in like high school algebra or something. But if you've forgotten, which many people do, that's okay. We'll refresh it. And you'll just have extra work to do in Alex to master those techniques for this class. All right, so if you want to determine x and y intercepts of a function, your x-intercept, you say, let me set my function equal to 0. And that's where it's going to cross the x, right? If you think about that, that is my function. When y equals 0, I'm crossing the x-intercept or the x-axis, right? Let's look at it graphically. So here's my thing. If I have a graph that looks something like that, let me make it a little more over here. Wherever I cross the x-axis, my y value right here is equal to 0. Okay? Wherever I cross my x value or my y-axis, my x value here is equal to 0. Okay? So this is where we let x equal 0, and the other one, we let y equal to 0, and so on. Okay? So let's do x-intercept. Okay, so x-intercept, we are letting y equal to 0 or f of x equal to 0, either one. So we take our function. Our function is x squared minus 4, and we set it equal to 0, and solve. So we add 4 to both sides, and we get x squared equals 4. I don't want to use blue because I'm using that for the other. Let's take the square root of both sides. Anytime you take the square root of a number, both the positive and the negative are true, make it true. So this would be x is equal to positive and negative 2, right? Think about that. Positive 2 times positive 2 is positive 4. Negative 2 times negative 2 is positive 4, right? Both of those make that statement correct. Okay? Therefore, we have two places that this function crosses the x-axis. You have it where you have positive 2, y is 0, and at negative 2, y is 0. So if you're looking at this on a graph, this is negative 4. Let me one, two, three, 4. So this is here and 1, 2, 1, 2. So it's saying that we cross at negative 2, 0, and positive 2, 0. So that's what that graph looks like. Okay. Now let's look at our y-intercept. Okay. Our y-intercept, let's do in blue. Okay. And remember, for our y-intercept, we're going to let x equal 0 and solve. So our function here is x squared minus 4. So we have x squared minus 4. And we're going to do this for f of 0. So we're going to let x equal to 0. So that gives me 0 squared minus 4. So that means I am at the point my y equals negative 4 when my x equals 0. So I have an intercept at 0, negative 4, and that's this point right here. And we can go back to the greens for our 2x intercept. Okay. Question. Okay. So this next problem, we have that g of x equals 3 minus the absolute value of x. So when we're looking at our x-intercept, again, we're doing y equals to 0. So we have 3 minus the absolute value of x equal to 0. We can add the absolute value of x to both sides. That's going to give me 3 equals the absolute value of x. So I know that x can be plus or minus 3 because the absolute value of positive 3 is 3. The absolute value of negative 3 is also 3. Okay. So that means I'm going to have an x-intercept at 3, 0 and negative 3, 0. Similarly, we could do our y-intercept. Remember, we want to set x equal to 0. So we're looking at f of, or in this case, g of 0 equals 3 minus absolute value of 0. And so that simplifies to 3. And so I have a y-intercept when x is 0, y is 3. Okay, question. Last example of this kind, we have h of 2 minus the square root of x. So we have, again, let's look at our x-intercept first. So we have 2 minus square root of x equals 0. We can add the square root of x to both sides. So we have 2 equals the square root of x. Now, to get rid of that square root, we need to square it. So whatever you do to the left-hand side, you have to do to the right-hand side and vice versa. So this is going to give me 4 equals x. And therefore, I have that 0 at x equal 4 when y is 0. Question. Last one is our y-intercept. And so for this one, we're going to say h of 0 is equal to 2 minus the square root of 0. Square root of 0 is 0, so that is 2. So when my x is 0, my y is 2. Okay, question.
Excuse me, Professor, do you mind going over the how you found the x-intercept again? I got confused.
The x-intercept, you
Yes,
set
ma'am.
the whole equation equal to 0. So for the x-intercept, it's either a lot of times you could say it is, I wrote it as y, but it's the same as f of x is y. So you set the whole function equal to 0 and solve for x.
Okay, thank you.
All right, so now let's do a couple of looks here where we want to determine what is our domain and range. Remember, our domain is what values x can be, and our range is what values our y can be. Okay, so when we're looking at the domain, in this case, my x, you can see this is going to go off all the way into infinity in both directions. So my x is not restricted at all. I could go from negative infinity to positive infinity. Okay. But what I am restricted with is right here, I only have y above that line, right? Well, that line occurs right here at this point when y equals 2. Okay. So my range is going to be when I have, it can equal 2 and it can go all the way up to infinity. Notice, infinity always gets parentheses because I can't ever actually get to infinity. Because as soon as I think I've reached the last number in line, there's another number and another and another and another and another and another, and it just keeps going forever. Okay, so I can't ever actually pinpoint it. So I can't actually land on it. So it's always a parenthesis. Or it would have hollow dots if it was on like a number line. It would have a hollow dot, something similar to this, right? Meaning I can't actually get to it. A bracket, this piece right here, is if it is included. So if I had a solid dot like I have here, or if it's included, I would get a bracket. Okay. So let's look at this next example. So pointing out here, I have a hollow dot and a solid dot. So how does that impact us? Well, let's look at the domain first. So this is saying this line's going to go off here. That means my x value goes all the way up into negative infinity for my x's, right? No matter how far here I come, at some point I may have to go up really, really high into the y, but I will have that graph represented. Okay. And the same over here. This is going to go off. It's going to keep growing and growing and growing. So again, my domain is going to be negative infinity to positive infinity. My range, on the other hand, again, these arrows, they're going to go up, up, up until forever. But where I'm limited is this point right here, which happens at y equal negative 10. You say, but what about this space where I'm jumping from one graph to the next? Well, that space is actually covered by this graph. So I don't have a jump in the graph here. So my range for this graph will include negative 10, and it'll go all the way up to positive infinity. Okay? Question. Got a couple of more graphs just so we can make sure we understand. Okay? All right. So looking at our domain, this goes all the way out to negative infinity. This one, notice there's no arrow, so it means it stops. It stops at this value right here, which is x equal to 4. Okay? So my domain can be any value from negative infinity up to positive 4. Bracket on the positive 4 because it can include positive 4 because I have a solid dot there. If that had been a hollow dot, I would have put a parentheses around the positive 4 to signify that it's all values up to that, but not including that value of 4. Okay. Now let's look at our range. Our range is our x value. So our x value can be this right here, right? And that is not our x value, our y value equal to 1. And then here and everything above, but stopping here because it can only go here and below, right? So it's really just looking at the graph. How are we constrained, right? So we can be any value of 1. Since it's a single character, we put it in these little squigglies. So any x that's 1, like any value of x, we could get a value of y, right? So we have all these values here. So y is in our range. Or we can also go from this is y equals 2 to y equals 8. So we can be anywhere between there. We could find a part of a graph somewhere that is in that. So the 2 is inclusive because of the solid. The 8 is inclusive because of the solid. So we get a bracket from positive 2 to positive 8 with brackets on both. Okay? Questions? I don't know how that got off. Let's say that's a dot. Okay? So now on this last example that we have here, if we're looking at our domain, what values can our x be? Our x is here, which is x equal negative 4. And you can see this tells us here that it'll go all the way down to negative infinity. Actually, I said negative 4. This is a negative 3, so this is negative 2. Okay, so our domain then is, when it's a solid dot, we've already did a solid dot. Let me put a hollow on here. Right, so let's put a hollow dot here. Okay. If that's hollow, that means everything up to and around it is included, but not that point itself. So in this case, we'd have a parentheses, -2 all the way to infinity. So our x could take on this -2 value, and then it can go all the way out to positive infinity. Okay. And lastly, our range. Our range it's right here. It's hollow though, right? So we can't do that. But this is telling me it's going to go on down here for infinity. So my y goes to -infinity, but it's capped off here. It has to be less than y equal to 4. Okay. So my range can go from -infinity, right? It can be any lower number as far down here as we want to go, but it can only be as high as +4. It can include 4, so we put that bracket on. Okay. Yes, there's only, well, there could be, if we had, technically there's only one domain, but you could have a U and something else here, right? So you wouldn't say domain this and this and this. You would use the little union symbol like we did here for this range. So it could be broken up. Did that help, Abdullah? Okay, perfect. All right, so the last bit of information I have from this section, and then we'll move into section 1.6, is we want to use the graph of the picture here to answer these questions here on the left. This is going to be something that you really want to be able to do because you're going to see something similar to this on your exam. Okay, so when I give you this and I tell you that this graph is of y equals f of x, answer these questions. So where is what is the value for f of -3? Well, that is really just telling you f of -3 is saying when x is equal to -3, what is y? So you would come over here and you would say, here's -1, -2, here's -3. What is my y value here? That's 1, 2, -3. So this solution would be -3 because I go find -3 for x and tell me what is my y value. Okay. Similarly, if I look at 0, here's 0 and here's this point. So when x is 0, my y is what? My y is equal to 2. Okay. Question. Okay. So for this next one, I want for all x, which f of x equals 1. Remember, f of x is really just y. So that's saying, where is y equal to -1? So I come over here and I'm like, here's y equal to -1. What are my x values? Well, that crosses right here where x equals -1. Okay. Similarly, I want to list out all my x values where my function is equal to +1. So I come here and that's this. This is a hollow, so that is not included. Okay. This is a solid, so it is. And so that is going to be where x is equal to 2. Okay. Don't include the hollow dot. I'm gonna erase that hollow dot out just so that it doesn't muddy up the picture for you. Okay. Now we want to determine the x-intercepts. X-intercepts, where does it cross my x-axis? None, right? I don't have any x-intercepts. What about where does it cross my y-axis? Right? And that occurs at this one location here. That is the location of 0, 2. Okay. And then when we determine our domain here is we're going from negative infinity to positive infinity. So we have that. And then our range, which color can we use? Let's use brown. Our range is going to go from negative infinity, right? Negative infinity up to 1, right? So we have here, it has to be less than 1. So it's going to go from negative infinity to 1. It can include 1, or not 1, negative 1. It can include it. Or then we have a little gap jump here, or it can go from here up to positive infinity, which is at positive 1 and infinity. Again, we get to use the bracket because we have this one piece right here that says it is part of the solution, the solid dot. Okay, question. Okay. All right, so this next section, we're going to look at graph transformations. So that you don't have to go digging in your textbook and I'll have to tell you, oh, go to this page in your textbook and look at this graphic or whatever. I put these parent functions, these are what we would call parent functions here in this thing that I'm going to export to PDF for you all so you don't have to go hunt it down. Okay. So there's linear functions, constant functions, there's square root functions, cube root functions, all of these. So basically, these 9 graphs, we're going to do transformations on. So if I know what the parent looks like, knowing how an equation may be shifted, I can go, oh, I don't have to replot all of those points. I know that my absolute value function looks like this v centered at 0, right? If I wanted to say shift it to the right 3 units, I can shift it 1, 2, 3 units and know that it behaves exactly the same, right? Everything else stays the same except my focus point. Okay, and so that's what this chapter is going to be about, is how do we do these transformations on these parent graphs. Okay. All right, question. Okay, so first of all, 2 of the more common transformations are if we look at vertical shifts or horizontal shifts. So a vertical shift is, am I shifting left or right? And a horizontal shift is, am I shifting up or down? Okay. And so if I have my function, and then I have this plus c, which is a constant, or minus c, which is some constant, then that's going to tell me, the plus tells me I'm shifting up, the minus tells me I'm shifting down. Okay. Horizontal, if the shift is part of the function, not in addition to the function, then minus h, I'm shifting to the right, plus h, I'm shifting to the left. Okay. So let's look at this in terms of, so really when we know these transformations, if I know the transformations, I don't need to build this table. I don't need to plot out 5, 10 points per graph. I could just go, oh, the parent looks like this with these modification transformations. I can shift it like this and do it in a matter of seconds versus plotting every single point. Okay, but to illustrate every single point, I am actually going to show you that, okay? So first of all, if we let X values be 0, 1, 2, 3, and 4, I plug those into my parent function, which is the square root of X. Square root of 0 is 0. Square root of 1 is 1. Square root of 2 is the square root of 2. Square root of 3 is the square root of 3. And square root of 4 is 2. Okay? So if we come back over here and we look at our square root function, you'll see that it doesn't come on this side, right? Because I can't take the square root of -1. It's imaginary. So I can only do the positive X values. So that is at 0, it's 0. At 1, it's 1. At 4, it's 2. So that is what my parent looks like. I'm going to put it just on both of these. One, two, three. I actually did that one too many. So here's 1, 2, 3, 4. Okay, so parent is in purple. Now we're going to add 2 to our parent. So 0 plus 2 is 2. 1 plus 2 is 3. Square root of 2 plus 2 is 2 square roots of 2, which is approximately 3.4. We need to know that to be able to plot it. Then we have the square root of 3 plus 2 is approximately 3.7. And 2 plus 2 is 4. Okay, so we can plot that. We have 0, 2. We have 1, 3. We have 2, 4. So you notice every single point was shifted up 2 units. Okay? Question. Let's look at if the plus had been inside of the equation. Okay? So now, instead of taking this final answer and just adding 2 to it, we actually have to put it all together. So this gives me 0 plus 2 is the square root of 2, which is approximately 1.4. This one is 1 plus 2, so that's 1 plus 2. This one, I'm going to spell it out a little better. 0 plus 2. So this is approximately 1.7. This is the square root of 2 plus 2. So that's going to be the square root of 4, which is 2. This one is going to be the square root of 3 plus 2, which is 5. So the square root of 5 is approximately 2.2. And finally, we have the square root of 4 plus 2 is approximately the square root of 6, which is 2.4. Okay. So now we have at x equal to 0, we have 1.4. At 1, we have 1.7. At 2, we have 2. At 3, we have 2.2. And at 4, we have 2.4. Okay. Now, had I plugged in a -1, right? If I plugged in a -1, that would have given me -1 plus 2, which equals 1, right? And if I had plugged in a -2, that would have given me -2 plus 2 equals 0. So here I would have been at this point, and here I would have been at this point, right? So that we can get the full look of that. And ultimately, what that is saying is I've shifted this direction 2 units, 2 units, 2 units. So I've shifted left 2 units every point. Okay? Question. So if I had known that my parent function is the purple one, would it not have been way easier to go, oh, this is +2, it's inside the function. That means I'm moving to my left, right? Because really, our standard function is x minus -2 because it's the minus, right? Whatever that value is. And so that tells us we're going in our minus direction. We'll get more into that as we progress, though, that ideology. Okay. So when that's positive, that means we're moving to the left. When it's x minus a value, we're moving to the right. That many units. Okay. So for this next one, I'm not going to put it as much, you know, how I did square root of 2 plus 2, square root of 3. No. So I'm not going to really do that much this time, but I will fill in the table here for you. Let's do purple. Let's stick with purple for our parent. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Okay, so we come in here, 0, 0, 1, 1, 2, 1, 2, 3, 4, and then we kind of get off the charts. But it's the same as if I put in -1, I'm going to get +1. If I put in -2, I'm going to get +4. So my parent function here and it'll go on into infinity. I'm just going to copy that, paste it. So our parent function is on here in purple. Our pink for our, so first, if we're minusing, that's just saying I'm going to shift everything down 2 units. So here, 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 here. So my new graph is going to look something like this. So let's plug in those values. If I plug in 0 squared minus this is -2. 1 squared minus, that's going to give me -1. 2 squared is 4 minus 2 is 2. 3 squared is 9 minus 2 is 7. 4 squared is 16 minus 2 is 14. Okay, so we come over here and we have 0 at the point 0, -2. Yep. +1, -1. Yep. 1, 2, 3, 4. You'd come over here, or at 2, you're at 2, right? So you can see they all line. But we didn't have to do all those math calculations. All we had to do was use our knowledge of graph transformation. Okay? Question. Okay, let's look at one more example. Now you can see this is within the parentheses, it's a negative. So that's going to tell me, the negative tells me I'm going to shift to the right. Okay, it's telling me I'm going to shift to the right. And we're going to shift to the right everything 2 units. So I'm going to go 2 units, 2 units, 2 units. This one, 2 units, it becomes here. 2 units, it becomes here, right? So my graph should look like this if I've shifted it 2 units to the right. Okay, so that gives me a value here of 41014. And so you can see at 0, I'm up here at 4. Yep. At 1, I'm at 1. Yes. At 2, I'm at 0. Yes. At x equal to 3, y is 1. Yes. And x equal to 4, y is 4. And so you could see those transformations without actually having to do the math calculation. Okay. Question. Okay. All right. So let's look at a couple of examples here. We won't spend a whole lot of time on these. But when we're looking at this and we want to determine, we have z equals x plus 1 minus 4. So we can tell our horizontal shift and our vertical shift, right? So our horizontal shift, that's positive. So that tells me I am left 1 unit. Okay. And because we have this -4 out here on the end, that tells me I am down 4 units. Okay. So if we had, what color did we use for purple? If we had had our actual graph in here, I'm not really going to graph all of this, but let's just say it was something, it's just our x squared is our parent graph, right? Something like this, not exact, but so what this is telling us here is that we can shift this down 2 units to this point, but we also want to shift it to the left 1 unit. So that would be our new starting point right here, and everything else would fall in line the same. Okay. That kind of went up. Everything would be down 2 over 1, and so that graph would look something like that. Okay, that transformation. Okay, question. All right, so this next one, this is an absolute value. So this negative in here tells us that we are going to go right 2 units. And this plus here tells us that we're going to go up 3 units. Okay? And that's off of our absolute value. So the absolute value is just, it goes right in the crease of all of those. Okay? And so when we are shifting to the right 2 units, and then we shift up 3 units, this is your new start point for your whole graph. Okay? So we didn't have to sit there and calculate, well, what is x1, x2, x equal to 3, x equal to 4. We can do those transformations based on the rules that we know. So Josefa, you say y to the right and not the left. On which one? This one that we're on or the previous one? Because that negative there tells us, right? If you recall back here, right here, if it's minus, we're shifting to the right. And if it's positive, we're shifting to the left. So since that is minus in here within the function itself, that's why it's to the right. And we'll see later, our standard form is x minus, c, which is some constant number. That's standard form. If you think of it that means we're in the right. I mean, this is how I think of it, right? In my mind, that means we're in the right form. We move to the right. Because standard form, we'll see later when we deal with like circles and things like that. Standard form is x minus h or x minus k. And that it all ties together. We're just not really ready for that part of the lesson this early in the course. Okay. All right. So next, just for the sake of time, because I spent a little extra time going over how to do things in Canvas and getting to Alex and stuff, I'm not going to cover filling in the table, but I am going to give those values to you all, okay? But we're not going to talk through each of the individual calculations. So, but the next type of transformations that we're looking at is we're going to look at vertical shrink and stretching, okay? And so what that means is when we're looking at that, if the value in front of ours, so if our function is here and we have some value in front of the function, right? So if we're looking at just x, that is our function, our parent function. But if I throw a 3 in front of it, now I'm going to shrink or stretch depending on if that a is greater than 1, or if it's between 0 and 1. So we're not talking negative here. Basically, we're talking, is it a whole number or is it a fraction? Okay. Or like, is it 1/2, 1/4, 1/3, such so forth. Okay. And so it'll depend if we're stretching it or shrinking it. Okay. And the same for the horizontal. If the a inside the function is greater than 1, then it's going to get shrink. And if it's, or when you think of shrink, you could think kind of gets smushed down, or it gets stretched out. You think you're stretching your arms up and you get a little more tall, so to speak. Okay. So let's look at that in action. So here you see we have 1/4, so our A is less than 1, right? Since our A is less than 1, it means we're going to have a shrink. It means we're going to get smushed, so to speak. Okay. And so if I had a 0, this would be 0, 1, 4, 9, 16, right? Just plugging in all the X inputs into the formula and getting that output. When I do a fourth of that, that's 0, 1/4, 1, 9/4, and 4. Okay. So if I do my standard function, 0, 1, 1, 2 is going to be up here at 4. So 1, 2, 3, 4. 1, 2, 3, 4. So this is just my parent function of x squared. Okay. Now I am going to add to it this transformation, my vertical shrinking. Okay. So that is 0. It's still here. But now at 1, instead of being up here, I'm shrunk down to here at like 1/4. It'll be on both sides, negative and positive, because it's like a mirror, right? At 2, instead of being all the way up here at 4, I'm only going to be here at 1. Okay. And at 4, so that's 2, 3, 4, I'll be at 4. 1, 2, 3, 4. And those mirror on the other side. Okay. And I'm going to change this to purple because that's our original value. Okay. I'm going to copy these over. For our other graph as well. Now you will see that we have the 4, it's multiplied by, it's greater than, right? So here, actually we're still on this one. Our A is greater than 1, okay? So that's 0, 4, 16, 36, 64. When we go put those in, we're still here at 0, 0. At 1, we're all the way up here at 4. And at 2, we're all the way off the charts up here at 16. So we're going to come in something like this. You could see that we're much more stretched. So you could think of that as if you let your arms be this graph, right? We're kind of arms a little bit over our shoulder, but our shoulders are kind of out. But the bigger that number is in front of our x squared, the closer we're pulling our arms into our ears, and we're getting up there to make it a much tighter thing. So we're like stretching our arms up to the sky, and we're getting closer and closer to our ears with our arms. Whereas when we have it and we're getting smashed down, we're flattening out that curve to where if it's flattened out enough that we're going to end up like a straight line almost. Cindy, you may not use your calculator on these because you have to show all of this stuff on your exam. So how are you going to do that if it's on a calculator? Right? And on the exam, it'll say, what are these transformations and stuff? And so you have to be able to do that without a calculator. Okay. All right, questions? Okay, so now let's look at this next one. This next example, we're looking at doing it for the square root. Remember, our square root is 1. Square root of 0 is 0. Square root of 1 is 1. Square root of 2, 3, 4. Square root of 4 is 2. This gives us a clean portion looking. So that's what our original looks like. So how do we transform it? The values are 0, 1, square root of 5, square root of 6, square root of 7, because you can see our x values changed there a little bit. And we'll keep that the same for both graphs that we're going to look at. Okay, so the first one, we have the 5. It's 5 on the inside. So now we're looking at horizontal stretching or shrinking. And so this is going to be 0, square roots of 5, 5, square root of 30, square root of 35, if we just strictly do the math of it. And so when we graph that, we have 0, square root of 5 is a little harder to define, but we could do 5, which is 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay. And so what do we end up with here? It's a graph that looks something like this. And you can see how it's kind of more elongated up there. And so because we have that positive value where this one is still called a shrunk because it is, I will say for the purpose of this class, I will not ask you to tell me if it was a shrink or a stretch, just to do it, right? And so when we look at it in terms of the 1/5, right? So the 1/5 times x here. So this is really like saying 1/5 x, the square root of 1/5 x. This is going to be 0, square roots of 1/5, 1, square roots of 6/5, and square roots of 7/5. And so when you go plotting those, we have 0 here, but then at 5, we're here at 1, and you can see it's much more flattened out there. Okay? So again, oftentimes, no, you don't have to know if it's a shrink or a stretch. So, all right. So, any questions on how we could use a table, but it takes a lot longer than if we are able to use the transformation? Okay. So now I want to look at the graph. So if I have this graph and I want to take this graph and I want to transform it at 4 times or the 4x like we have up here, how do we do that, right? So first of all, let's just write all these points. We have this point -3, -1. We have a point -1, +1. That's this point. We have a point 4, -3, and a point 6, 3. Okay. So if we divide each x coordinate by 4, we will get our transformation. Okay. So this would be -3/4, -1. This one would be -1/4, 1. This would be 4 divided by 4 is 1, -3. And this one would be 3/2, 3. So now we can plot these points. And so we have -3/4, -1. We have -1/4, +1. We have 1, -3, and we have 3/2, +3. Okay, so this graph went from here to here to here to here. So you can see how this got compressed in because of that 4x there. It got squished in. Okay? Question. So that brings me to talk about reflections. And so we can either reflect across the x-axis or we can reflect across the y-axis, okay? So if our whole function, if it's negative and then the function, then we're reflecting across the x-axis. If our x is what is negative, then we are within the function, then we're reflecting across the y-axis, okay? So here we have this graph. Given this graph, we want to, how do I reflect the across the x, right? So this is telling me I'm going to reflect across the x-axis. And so my 0 still stays. Now this was 1, 1. Now I'm going to be at 1, -1. Okay. This one is 1, 2, 3, 1, 2, 3, 3, 3. Now I'm going to be at 3, -3. And this one is 4, 1. So now I'm going to be at 4, -1. So basically all my y values changed, right? So I have here, here, here. And that is that exact graph reflected on the the x-axis. So think of that as if I put a ink or paint on this line, and then I fold my paper on the axis in half, it gives me this replica right here. Make sense? Okay. Then, what if I said, well, what if I'm reflecting on my y-axis, right? Okay, so I'm going to reflect around the y-axis. So now I'm changing my x value. So here I'm still 0, 0. This was 1, 1. So now I am at -1, 1. This one was 3, 3. So now I'm -3, 1, 2, 3, 1, 2, +3. And my other one is 4, 1. So now I'm at -4, +1. And that looks something like this. And so similarly, if I had put paint on here and then fold it on the y-axis, it gives me this exact replica on the other side. Okay? Questions? Okay, so again, I'm going to post these notes, and so you can find this exactly in your textbook, or as Chelsea posted here, you can go in the modules under additional resources and get a copy of this shortly after class. It'll be posted there. So this is just a snapshot of what all the transformations that we've talked about tonight are. Okay. All right, so let's look at, we just have a couple of more problems and then I'll get you guys out of here. So first of all, sometimes functions require more than one, more than one, transformation. And so how does that work, right? And so here is an example. And it's an absolute value. So I give you, here's what the absolute value function looks like. Okay. And we want to perform these shifts on it. So what does that look like? Right. And so this right here, this +1, that tells me I am going to shift the graph left 1 unit. Okay. This 2 here is we're applying a vertical stretch because the A is greater than 1. So that's a vertical stretch. So what we do here is we multiply our Y values by 2. And then this -3 out here tells me that I have a vertical shift and I'm going to shift down 3 units. Okay. So coming here, we have this. When we incorporate, we want to shift left 1 unit, down 3 units, multiply our Y values by 2. We're going to end up with 0, 0, Y value. So we're going to shift down 1, multiply our Y value, and not down 1, sorry. We're going to shift to the left 1. Our Y value multiplied by 2, which still is 0, and then down 3 units. That's going to land us right here. Okay. If we took this point right here where we're 1, 1, we're going to shift left 1 unit, multiply, that was a 1, multiply that by a 2. So now we have a 2 for our Y value. And we're going to shift down 3 units. Okay. And we can go through this, each of those, and we'll get our stretches and our shrinks, but ultimately this will look about like 1, 2, 3. 1, 2, 3. We'll have a point about here and around 1, 1. So that is what those green transformations would look like on the parent function of the absolute value. Okay. Question. All right, one last example for you all. And this one is the parent function of the square root. Okay, so we have a few things. This negative here tells me that we have a reflection, right? This 1/2 here tells me that we have a vertical shrink. Actually, I'm gonna keep those, but I want to rewrite this problem first. See how we don't have the x first? So I want to rewrite this as negative 1/2 square root of negative x plus 3. Okay, so this one's a little bit wonky. It's a little crazy. Let's take that back over here. Okay. This negative right here, that tells me that I have a horizontal reflection. Okay. And lastly, this plus 3 tells me that I have a horizontal shift. Okay, of 3 units. So ultimately, one, 0 here, 4, 2. This is what our parent would look like for our square root. When we do all of these shifts, we're reflected, we're shifted, we're horizontal shift 3 units. So let me change the color. We're horizontal shift 3 units. We end up with a graph that looks something very similar to this. You guys won't have to do anything like this. I'm just trying to show you how you might be asked to decipher from one of these what is going on. But you wouldn't have to do reflection within a reflection within a shrink and you know what I mean? Like you will have more basic ones, but I just want to show you how we didn't have to plug in things. We can take the knowledge that we have to make those transformations. Okay. And so that's what I want you guys to get into the habit and practice of with this section is making sure that you're not relying on doing all the calculations. You'll run out of time on the exam if you heavily rely on doing the calculations and building the tables versus using the transformation. Okay. All right. So that is all the material I have for you all this evening. Remember, if it was a lot, if you want to rewatch it, anything like that, by tomorrow afternoon, if you don't see the video available in your Canvas, then shoot me an email to remind me, because chances are, because this class did go it's gone at 3 hours tonight, it'll take Zoom quite a minute to make that available to me. And unfortunately, a couple of years ago, they changed it to where I can't just say publish it when it's ready. I have to wait till it's ready and then I can go publish it. So it probably won't be until tomorrow that you guys can rewatch the video. But tonight I will upload these slides that I have done in the PDF form for you all. Josefa, it says, what if some of the points are a little off because we didn't use the tables? Yeah, that's completely fine. I'm not expecting perfection. When you are doing it in Alex, they will probably be problems that are not midpoints and such. So you should be able to graph with the estimations. But on the exam, I just ask that you label your graphs. So you know how this one, it has these points so if you have graph paper, that would be great for an exam. Or otherwise you just have to very carefully label your graphs so that I know what you're talking about. Any other questions? All right, that is all of the material I have for you all this evening. I will see you next Monday. Don't forget you have 4 things that are due on Monday. 2 of them in Alex, 2 of them in Candace assignment. Okay? All right, you guys have a good evening, and if you have any questions, just shoot me an email.
Thank you. Good night.
You're welcome. Thank you. Have a good night.
Thank you.
You're welcome.